This is the second part of the 28th lecture in the series Mathematical Methods for Economics. In the first part, we had introduced the general definition of elasticity. And in this part, we will now look at how to work our way through this definition. In particular, we will look at some rules relating to elasticities. We will also look at how we can use the general formula to calculate specific elasticities in economics. We have already looked at the calculation of the own price elasticity of demand in the first part of the lecture. And in this video, we will take up very briefly the income elasticity of demand and the elasticity of supply. We'll just define them. And but the thing is, we need not restrict ourselves to just these elasticities. In fact, once you have the general formula, the general definition of elasticity in place, you can just apply it to the calculation of any kind of elasticity. So, to just have a quick recap, in the first part of the lecture, in the first video, I had set up this general definition of elasticity where you have a variable which is a differentiable function of x. So, you have y as a differentiable function of x, y is equal to f of x, and if f of x is not equal to 0, we have the elasticity of the function f with respect to x defined as the derivative of f with respect to the function with respect to x, so that is f prime of x times x divided by f of x. Now, let us apply this definition to a problem here which asks you to calculate the elasticity of f of x, which is given by a times x to the power of b with respect to x. Here in this function, a and b are constants and a is not equal to 0. So, if we had to calculate the elasticity of f of x with respect to x, we use a formula here which is f prime of x times x divided by f of x. So, f prime of x is given for this function as a times b times x to the power b minus 1 times x, and then that is divided by f of x, which is nothing but a times x to the power b. Now, you can see here that the a in the numerator will cancel out the a in the denominator, plus the numerator can be written as x to the power, you have x to the power b minus 1 here, and if I take this x to the denominator, I have another x to the power b minus 1 in the denominator. So, that will then cancel out the x to the power b minus 1 in the numerator, and what you are left with as the elasticity of the function with respect to x is b. In fact, this is a very important result, because if you notice here, this function is a power function, and we have the result here that the elasticity for a power function is a constant. In particular, the elasticity for a function that takes this form ax to the power b, that is nothing but the exponent that you have here for x, that is b. In fact, if you go back to the calculation of the price elasticity of demand in the first video for elasticity that we have, there I had taken the demand function which was 10 times p to the power minus 0.75, and again if you just apply the logic that I just gave you here, the result that I just gave you here, that the exponent is the elasticity. So, here for the example that we did in the previous video, we got minus 0.75 which was speed. So, we had the demand function 10 times p to the power minus 0.75, and we got minus 0.75 only as the price elasticity of demand. So, that's just a quick cheat sheet for you if you ever have to calculate the elasticity for a function like this. Now, also to summarize the results, some results for elasticity. And here, because we have elasticity of a function or elasticity of y with respect to x as the percentage change in y divided by the percentage change in x, then we can say that if the absolute value of the elasticity of f of x with respect to x is strictly greater than 1, then the function is said to be elastic at x. This is because if the elasticity of the function with respect to x is strictly greater than 1, then the percentage change in the quantity demanded is going to be strictly greater than the percentage change in price, and that makes the function elastic at the percentage change in y would be strictly greater than the percentage change in x, and that makes the function elastic at x. Then if we have the absolute value of the elasticity being 1, we say that the function is unit elastic at x. If the absolute value is strictly less than 1, we say the function is inelastic at x, because in this case the percentage change in y is going to be less than the percentage change in x. If you look at the next result, if the elasticity of f of x with respect to x is 0, this is a case where we say that the function is perfectly inelastic at x. And finally, if the absolute value is infinity, then we say that the function is perfectly elastic at x. These are important results, so please keep these in mind. Let us now look at this example where we will bring in this kind of a result that we just put up on the previous slide. Here we have d of p, which denotes the demand function for a product, and by selling d of p units at price p, the producer earns revenue r of p. So the total revenue is given by r of p, which is equal to, it's nothing but the price times the quantity, so p times d of p. Okay. The question then requires you, this example requires you to calculate r prime of p, which is basically nothing but the additional revenue generated due to an increase in p. So r prime of p is the marginal revenue with respect to price, vis-a-vis price, and that for that we can use a product rule, which is then going to give us r prime of p as the derivative of p times the second variable. So that's going to be a derivative of p with respect to p is 1. So that times the second variable, which is d of p, plus p times d prime of p using the product rule. Now here I can take d of p common. So the marginal revenue generated due to an increase in price can be written as d of p times 1 plus, because I have taken d of p common, I get 1 plus p divided by d of p times d prime of p. And if you notice here, p divided by d of p times d prime of p is nothing but the price elasticity of demand. So I can write r prime of p as d of p times 1 plus the price elasticity of demand at p. Now, suppose I have to calculate the elasticity of revenue with respect to price, then the elasticity of revenue with respect to price, again using the general definition, is going to be r prime of p times p divided by r of p. Now, r prime of p I have already derived for you from the previous slide. But what you can see here is that this is now going to give you the elasticity as r prime of p, which is nothing but d of p times 1 plus elasticity of demand with respect to price, and this is then divided by d of p. Let me just back up. This p divided by r of p, because your total revenue is p times d of p. So p divided by r of p is going to be nothing but 1 by d of p, right? Because r of p by p is d of p. So instead of p by r of p, I am just substituting from the first equation 1 by d of p, and this is how I get the elasticity of r of p with respect to p as r prime of p divided by d of p. So r prime of p we have is from the previous slide is d of p times 1 plus the elasticity of demand with respect to price, that is divided by d of p, and d of p will get cancelled in both the numerator and denominator to give us the elasticity of revenue with respect to price as 1 plus the elasticity of demand with respect to price. So this is the result we have, and we have now written elasticity of revenue with respect to price as r prime of p divided by d of p, the demand, which is then 1 plus the price elasticity of demand. Now, because the demand curve is downward sloping and it's going to give us dq by dp as negative, so d prime of p is going to be negative. So, it is customary to express this expression in terms of an absolute value, because by looking at the absolute value, we are able to compare things better. So, an alternative way of writing the elasticity of revenue with respect to price is to write things as 1 minus the absolute value of elasticity of demand with respect to price. And you can see here the two expressions that we have on this slide are actually the same, because all I have done is that I have taken the absolute value of the elasticity of demand with respect to price, and the negative sign that I had because this elasticity would be negative, I have just brought it out of the absolute value and written things in this way. This actually helps us arrive at some interesting results, which you can see as follows, because once I write the elasticity of the revenue with respect to price as 1 minus the absolute value of the elasticity of price elasticity of demand, I can now, this now lends itself to interesting interpretations. You can even do it with the numerical values, but this just makes with the absolute values, the interpretations are easier. So, if the price elasticity of demand is in absolute terms is 1, which is to say that you have unit, the function is unit elastic at p, then what we have here is, because if the absolute value is 1, then dr by dp is going to be 0, because the elasticity of revenue with respect to price is dr by dp times 1 by d of p. So, r prime of p is going to be 0, because d of p can't be 0. So, r prime of p is nothing but dr by dp, and this is to say that when the price elasticity of demand at a point is equal to -1 or 1 in absolute terms, a small price change will have almost no influence on the revenue. In fact, these are results that we cover a lot in microeconomics, and we're just summarizing them here. Further, if the price elasticity of demand in absolute terms is more than 1, which is to say that demand is elastic, then in that case we have that when price increases, that is going to lead to a fall in the revenue, in the total revenue. So, if demand is elastic, so demand is going to be very sensitive to change in price. So, if price increases, that is going to lead to decrease in revenue for the producer. Similarly, if demand is inelastic, which is to say that the price elasticity of demand is less than 1, strictly less than 1 in absolute terms, then dr by dp is strictly greater than 0, it is positive, which is to say that when price increases, that is also going to cause the total revenue to increase. And this is a very important set of results that we have here. Another kind of elasticity that I would like to introduce here, because we have set up the general definition of elasticity, but let us see how we can apply the general definition to calculate other kinds of elasticities, specific elasticities that we use in economics. And one such elasticity is elasticity of supply. So far we have looked at the price elasticity of demand, we have looked at the elasticity of revenue with respect to price. And this is yet another kind of elasticity, supply elasticity. Let us suppose the supply function is given by Q equal to S of P. So, Q represents here the quantity supplied, and that is a function S of P. Here the elasticity of supply with respect to price is then given by, again using the general definition, that is going to be given by S prime of P, which is nothing but dq by dp from the supply curve times p divided by S of p. So, you can just, the general definition just makes things very straightforward. You can just apply it as long as you know how one variable depends on another. Let us now look at an example which helps us understand what is income elasticity of demand, or the Engel elasticity. Here we have the commodity apples. So, the demand for apples in the US as a function of income R for the period 1927 to 1941 was estimated as d equal to a times r to the power 1.23. Here a is a constant, capital A is a constant, and the question asks you to find and interpret the elasticity of demand with respect to R. Note here that the elasticity of demand with respect to R here is called, by definition, it is the income elasticity of demand or the Engel elasticity. It tells us how demand responds whenever there is a change in income. And as I have already told you that for a function of this kind, it is this power 1.23, which will represent the elasticity. You can also calculate it yourself to check, to double check. So you can see for yourself that you can calculate for yourself that the income elasticity of demand, the elasticity of demand with respect to income, is going to turn out to be 1.23. What interpretation does this lend itself to? This simply says that if there is a 1% increase in income, this will lead to an increase in the demand of approximately 1.23%. So this would then mean that what we have here is a normal good, because for a normal good, when there is an increase in income, that is going to cause the demand curve to shift to the right. So the demand will increase at each price, and that is to say a 1% increase in income will lead to an increase in demand also. In this case, it is an increase in demand of approximately 1.23%. And if it leads to a decrease in demand, that's going to be the case of an inferior good. Let us move on to the next example. In this example, we talk about a study of Norway's state railways, which reveals that for rides up to 60 kilometers, these are relatively shorter rides, the price elasticity of the volume of traffic is approximately minus 0.4. So according to this study, the question asks you, what is the consequence of a 10% increase in fares? And here, this is similar to the question, the statement that I talked about vis-a-vis candy. So here, if there is a 1% increase in railway fares, that's going to lead to a decline in the volume of traffic by 0.4%. So if there is a 10% increase in fares, that is going to lead to an approximately 4% decline in the volume of traffic. Now, the study further reveals that for rides, for journeys, for rides over 300 kilometers, the corresponding elasticity is approximately minus 0.9. So what we have here is that for longer journeys, the elasticity is larger in absolute value than for shorter journeys. And the question asks you, could you think of a reason why the elasticity is larger for longer journeys vis-a-vis shorter journeys? And here we could think of a situation like this, where for longer journeys, you might have access to substitutes like air travel. So if substitutes like air travel are available, substitutes to railways as a substitute to railways, then in this case we could have a situation where the elasticity for journeys which are long are relatively higher. We will now, in the last segment of this video, we will look at some rules for elasticities, and these are extremely helpful rules. So here we have, let us suppose f and g are differentiable functions, and capital A is a constant. So here we have, and I'm going to just apply the same definition to every rule. So I'll just go through a few of these. The rest of these you can calculate on your own. So the elasticity of a constant with respect to x is going to be 0, because when I take the derivative of the constant with respect to x, here our function is nothing but capital A. So f prime of x will be 0. So elasticity is going to be 0. Elasticity of f times g is with respect to x is given by the elasticity of the function f with respect to x plus the elasticity of g with respect to x. Now to prove this, let us suppose we have a function t of x, which is our f of x times g of x, or f times g. Then the elasticity of t of x with respect to x is nothing but t prime of x times x divided by t of x by definition. and t prime of x is by the product rule equal to f prime times g plus g prime times f, and this whole thing is multiplied by x divided by t, which is f times g. This then, because the g will cancel out in the first term in the brackets with the g outside in the denominator, so that leaves us with f prime by f in the first term plus g prime by g, because the f will get cancelled and the whole thing will be then multiplied by x. So this is nothing but elasticity of f with respect to x plus elasticity of g with respect to x. Similarly, you can also prove that the elasticity of f divided by g with respect to x is elasticity of f with respect to x minus elasticity of g with respect to x. The next rule says that the elasticity of f plus g with respect to x is f times the elasticity of f with respect to x plus g times the elasticity of g with respect to x divided by f plus g. So again, to calculate the elasticity, let us set up this function t of x, which is f of x plus g of x. Then the elasticity of t of x with respect to x is t prime of x, which is nothing but f prime plus g prime times x divided by t of x, which is f plus g. And now what I have done is I have taken 1 upon f plus g out up front, and then I have f prime divided by f prime divided by f times f plus g prime divided by g times g. I have just multiplied and divided by f here in this first term in the brackets, multiplied and divided by g here, the whole thing multiplied by x. And now you can see for yourselves that this is nothing but, because f prime by f times x or f prime times x by f will be nothing but the elasticity of f with respect to x, which is then multiplied by f. So that is what I have in the first term here in the final result in the numerator, and the second term becomes g prime times x by g, which is the elasticity of g with respect to x, and that is multiplied by g. So the end result is what we just spoke about, which is exactly what we have in the rule here. Similarly, we can also derive this result, that the elasticity of f minus g with respect to x is the elasticity of f with respect to x times f minus g times the elasticity of g with respect to x divided by f minus g. And finally, we have this last rule that says that the elasticity of f of g of x, we have a composite function here with respect to x, is the elasticity of f of u with respect to u times the elasticity of u with respect to x, where u is equal to g of x. So let's calculate this. We have set up t of x as f of g of x, and elasticity of t of x is t prime of x, which is f prime of g of x times g prime of x times x divided by t of x, which is f of g of x, and once you go through these calculations, you get the desired result. Now let's see how we can use some of these properties to calculate. I've summarized the rules here. How we can use some of these properties, some of these rules to make our calculations easier. So if we look at this particular problem, it asks you to calculate the elasticity of y with respect to x for the equation y to the power 6 equal to x to the power 5. Now elasticity of y with respect to x is dy by dx times x by y. So if I have to find dy by dx, I differentiate both sides of this equation to get 6y to the power 5 dy by dx is equal to 5x to the power 4. This then gives us dy by dx as 5x to the power 4 divided by 6 times y to the power 5, and then I have elasticity of y with respect to x as 5x to the power 4 divided by 6y to the power 5 times x by y, and here this when I add the powers of x, I get 5x to the power 5 divided by 6 times y to the power 6, which is nothing but 5 by 6, because x to the power 5 divided by y to the power 6 from this equation on top is nothing but 1. Now finally, let's just do one more problem to conclude this lecture. Here this problem asks you, and this is actually a very nice application of one of the rules which involves the product of two functions, elasticity for the product of two functions. So here you have the equation y divided by x is equal to x plus 1 to the power a times y minus 1 to the power b. And this in turn implies that y is equal to x times x plus 1 to the power a times y minus 1 to the power b. So, elasticity of y with respect to x, because it's a product of three functions, that's going to be elasticity of x with respect to x plus the elasticity of x plus 1 to the power a with respect to x and plus elasticity of y minus 1 to the power b with respect to x. Now, elasticity of x with respect to x is nothing but 1. So, that's going to be the first term plus the elasticity of x plus 1 to the power a with respect to x plus the elasticity of y minus 1 to the power b with respect to x. Now, note here that the elasticity of x plus 1 to the power a is nothing but the derivative of x plus 1 to the power a, which is a times x plus 1 to the power a minus 1 times x divided by x plus 1 to the power a. And if you simplify, you get a times x to the power, a times x divided by x plus 1. Similarly, the elasticity of y minus 1 to the power b is the derivative of this expression y minus 1 to the power b times, which is going to be b times y minus 1 to the power b minus 1 times dy by dx times x divided by y minus 1 to the power b. So, here I can just simplify this as I am giving you the, you can work through these calculations because I am running out of time. So, the last step here gives you the result, which is just some algebra. So, b times y divided by y minus 1 times elasticity of y with respect to x. And now, let's bring all these results together. So, the elasticity of y with respect to x is 1 plus a times x divided by x plus 1 plus b times y divided by y minus 1 times elasticity of y with respect to x, and we collect the terms with elasticity of y with respect to x and get this expression here. And once we solve for that the elasticity of y with respect to x, we get this expression, which is x plus 1 plus ax divided by x plus 1 times y minus 1 divided by y minus 1 minus b times y, and this is our final answer. So, with this we conclude the second part of the lecture. Thank you.